Assalamu alaikum. Hope you're doing fine. We know conductors are the substance which allows electric current to pass through them. The passage of electric current through these conductors become possible due to the presence of charge carriers. In conductors, free electrons acts as charge carrier. What are these free electrons? We know almost everything in the universe is made of atom. These atoms have electrons revolving around the nucleus. Out of them, there are certain electrons which are loosely bound to the nucleus. These loosely bound electrons are free to move from one atom to another atom. We call such electrons as free electrons. When such conductor through which if we pass current, all these free electrons move in a particular direction. If one such current carrying conductor, when placed in a magnetic field, these free electrons experiences magnetic Lorentz force. As a result, the entire conductor experiences a force. Now we'll demonstrate this with the help of a simple experiment. For that, I have taken an aluminum foil strip whose ends are connected to crocodile clips. Okay. Now, to produce magnetic field, I have taken few powerful magnets that I am going to place at the bottom of this aluminum foil strip. As you can see, the north pole is facing upward. Okay, that means the magnetic field acts upward. Now, the yellow crocodile clip is connected to positive terminal of the battery. Then, the green crocodile clip is connected to negative terminal of the battery. Look at this carefully. What happens when I connect this green crocodile clip to the negative terminal? See? The moment I connect the current carrying conductor moves towards me. Here, as this end is connected to positive terminal, the current flows in this direction. The magnetic field acts upward direction, and the force experienced by this conductor, current carrying conductor, acts towards me. These three are mutually perpendicular to each other. Now I am going to reverse the current. See what happens if I do so. A yellow crocodile clip is connected to negative terminal, and green crocodile clip is connected to positive terminal. Look at this carefully. What happens when I do the connection? You can see, as I reversed the direction of flow of current, the force start moving in the opposite direction. It moves away from me. Okay. Now, I will reverse the magnetic field. I will show you what happened to the force. Okay. No force is active when there is no magnetic field. Now I reversed it. I am going to reverse the direction of magnetic field. Okay. When I did so, the force acts towards me. Now there is no force acting on this conductor, as there is no current flowing through it. I pass current. Force acts towards me. For better visibility, I place it this manner. Now I pass the current through this aluminum foil strip, which is placed in magnetic field. You can see it moves this manner. Now reverse the current. Reverse the current, aluminum strip moves away. This clearly shows that a current carrying conductor experiences a force when placed in magnetic field. Now I am going to get the expression for force experienced by a current carrying conductor placed in magnetic field. I consider a conductor. This was is considered as conductor. The length of this conductor is L. Length is L. And the area of cross section of this conductor is taken as A. Then I pass current I through this conductor. Suppose this is the direction of flow of current through the conductor. See, when I say I pass current, that means I have connected this conductor to a power supply or a cell. Oh, okay. Let's see. Connect this to a cell. Oh, having a positive and a negative terminal. This is the positive terminal. This is the negative terminal of the cell. Notice so, then current will flow in this direction. Current flows in this direction. Current flows from positive terminal towards the negative terminal. Okay. Now, due to this, free electrons present within the conductor. Electrons have negative charge. These electrons move towards the positive terminal. That means these free electrons are moving in a direction opposite to that of current, electric current. Remember this. Now when they move, they collide with each other, and they also collide with ions present in the conductor. So their velocity reduces as they move towards the positive terminal. We call this one as drift velocity. So electrons within the current carrying conductor travels with velocity known as drift velocity. Okay. Now we have studied long ago. We have obtained the expression between the relation between current I and drift velocity. Now I have taken a separate video on this. To get more information, kindly go through that video. I give the link in the description. So here I is equal to NAEVD. This is a relation between current and drift velocity. Now, suppose this conductor is placed in a magnetic field. I represent the magnetic field with this cross. This crosses represent the magnetic field. You remember this? When you come across this kind of symbols in a diagram, a cross or encircled cross, these two represents the magnetic field acting inward. Well, this represents the field acting inward. It may be magnetic or electric field. The next, suppose there is a dot, encircled dot really represents the magnetic field acting outward. Okay, the magnetic field is acting inward. So in the presence of this magnetic field, the moving electrons will experience a force. We call that force as Lorentz force. What do you call that? The force experienced by a moving charge in the presence of magnetic field is referred as magnetic Lorentz force. And we know the expression for magnetic Lorentz force. What is that? It's nothing but F vector. Here Q is the magnitude of the charge. So V vector cross B vector. This is the expression for Lorentz force. Okay. Now to make my work easy, what I do, I take a small element of this conductor. There is a small element I have taken, small portion of this conductor, whose length is dl. Length of this one is dl, through which current is flowing. I call this element as length element. Here dl is referred as length element. Clear? Now, the number of free electrons present in this length element is nothing but capital N. Okay. Then, if you look at this equation, you will find a small n here. Here, small n is nothing but number of free electrons present per unit volume of the conductor. Got it? And here, n is capital N is the number of free electrons present in the length element that we have taken here. We know volume V is the product of area and length. Here, length of this element is dl. This is the volume of this length element. Okay. Now I take it as such. Then, now from this expression, I am going to get the expression for force experienced by free electrons present in this conductor placed in the magnetic field. So from here, F vector is equal to, here in the place of Q, we have charge of the electron. Charge of the electron is E. Okay. And in the place of V, we have V D, which stands for drift velocity. V D vector cross B vector. Okay. This is the force experienced by each free electron in the conductor. Then, if we multiply this with the number of free electrons present in the volume of this length element, then we obtain the total force experienced by this length element carrying current I placed in the magnetic field. Okay. For that, I need to get the value of N. Okay. So I'll start with this. From here, N is equal to N upon V. From this, N equals to small n multiplied with V. I do cross multiplication. I take V that side. That will multiply. Clear? Then what is V? We know the value of V. From here, it is A D N. This is the expression for N. I box this. Then the force. It is dF. dF is the force experienced by length element dl. It is obtained if we multiply n with the f vector. Clear? Let me do that. Now I substitute the value of n. That is nothing but n a dl. And what is f vector is this. Let us see VD vector cross B vector. Now this provides me DF value. Now before going ahead, I rearrange it. How do I do that? See, it is rearranged as DF vector minus n is written outside. Then A E dl. And here then VD cross B vector. Oh yeah, from the diagram it is quite clear that dl, no, if dl, here, length element dl acts along the length of the conductor, length of the conductor. So here current element, right, ideal vector as the current element, and it is nothing but, you know the value of I, no, that I am going to substitute here, vector ideal vector. You know the value of this. See, what do I get if I do so? You know, then A, E, V, D. Now here I have vector notation. VD is a vector quantity, so I use a vector symbol here. Now one more thing I do here, E is the charge of the electron. Electron has negative charge, so minus sign is used here. Then what next? This is the value of I. Written here, then we have a DL. Then DL is this mentioned, DL vector. Alright. So now we just compare these two. Okay. We have to mention vector symbol here because this provides the direction to this part. Now, if you compare this one with this equation, you will find this part is NAE dl VD vector. NAE VD dl vector dl. This is equivalent to IDL vector. So this is nothing but IDL vector. So what I do, in place of this, I replace it with IDL vector. So this can be written as df vector equals to I dl vector cross B vector. This is the final expression that provides us the force experienced by the electrons present in this volume of the conductor. Okay. Right. Now, if you want to find out the force experienced by the entire conductor, then what you need to do? You need to integrate this. So, the force experienced by the entire conductor carrying current and placed in magnetic field is given as F vector equal to the place of dl. In the place of df I have written F, in the place of dl what I'll write? I'll write L. So IL vector cross B vector. Okay. Then vector form. I box this. Next, in magnitude, this can be written. We know. What do you know? You know that. If we have A vector cross B vector, then this can be written as AB sin theta. Then we have IL vector cross B vector. So this can be written as F equals to ILB sin theta. Okay. This can be rearranged. I have written this manner. Now F is equal to BIL sin theta. So I box this for better visibility. This is the final expression that provides us the force experienced by a current carrying conductor placed in magnetic field. Okay, now we'll discuss few special cases. What if this conductor is placed at an angle of 0 degree? When it will be at 0 degree, suppose I take case 1. if the conductor is placed parallel to the magnetic field. In such case, theta is taken as 0. We know sin of theta then become sin of 0, and sin of 0 is 0. So what happens if I substitute that one here? Substitute the value of F is equal to BIL sin of 0. Then what do I get? It becomes F is equal to 0. This shows that when the conductor is placed parallel to the magnetic field, the force experienced is 0. The conductor do not experience any force. And a second, case 2. Case 2. What if the conductor is placed perpendicular? Perpendicular means the angle is 90 degree. Theta is equal to 90 degree. Then what happens? Sin theta becomes sin of 90. That means 1. So F becomes equal to BIL sin 90. The sin 90 is equal to 1. So the value obtained is this. F equals to BIL multiplied with 1. So force acting on the current carrying conductor placed in magnetic field making an angle 90 degree is maximum. Here the force experienced is maximum. I repeat, when the conductor is placed perpendicular to the magnetic field, then it experiences maximum force given by this expression. Here, the direction of force is given by Fleming's left-hand rule. This is given by Fleming's left-hand rule. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.